So today we are finishing the chapter 3. So again, a quick reminder about what we've done on this chapter. So the first result was the Baire theorem, which appears here. Then, thanks to the Baire theorem and its corollary, we were able to prove the uniform boundedness principle. The open mapping theorem, and the closed graph theorem. So we are going now to review a little bit the closed graph theorem. So the closed graph theorem says that if you consider two Banach spaces E and F, and you have a linear operator from E into F, if you assume that the graph of T, that is x T of x for x in E, if you assume that it's closed in the product space E times F, then T is bounded. So the proof relies on some exercises that we did before, which themselves rely on the open mapping theorem, but so it relies on the following exercise. If you have a linear space and you have two norms on this linear space, and E is a Banach space for the two norms, and so if you have a bond like the norm of x is less than c times the norm of x2 is less than c times the norm x1, then we prove that you have the two norms are equivalent. That is, the norm of x1 is also less than a constant g times a norm x2. So that's this result that we are going to apply to prove the closed graph theorem. Because so we define the following norm on E. This is called the graph norm. So the norm of x2 equals norm of x on E plus norm of tx on F. So you see that the norm of x in E is less than the norm of x in 2. So we have one side of the inequality. So if you prove that, so E is a Banach space for the norm 1. So if you prove that E is a Banach space for the norm 2, then from the previous exercise, we will have also that the norm of x2 is less than d times norm of x1. So if you apply that, you get this inequality here. And with that, you put norm of xe on the other side. And this gives you what we are looking for. That is that the operator T is bounded. All right, so to achieve the proof, to complete the proof, we need to prove that effectively E is a Banach space for the norm 2. So you pick up any sequence xn in E, so a Cauchy sequence for the norm 2, then you can verify that xn txn is a Cauchy sequence in the product space E times F. Now, since E and F are Banach spaces, then xn converges in E and y and txn converges in Y, that is xy converge in, so that is x and t of xn converge to xy in this product space E times F. But since G is closed, we deduce that the limit belongs to G, that is y equals tx. So with that, it follows that, in fact, txn converges toward tx, which gives you that xn converges to x in E, endowed with the norm too. And that's the end of the proof. So to end the chapter, I propose an exercise which is an application of the bondedness, the uniform bondedness theorem, which is an important result in the theory of semigroups. So we don't need all the things for the theory of the semigroups, but just the definition of a C0 semigroup. So a family ST of bonded linear operators from a Banach space into itself is called a semigroup if it has the properties which are in fact the properties of the exponential at time t0, at time t equals 0, it's the identity, and you have that st plus s equals st applied to s of s. So this is a semigroup. If you add the fact that as t goes to 0, s of t of x goes to x, you call it a C0 semigroup. And if ST is a C0 semigroup, then you have this estimate, you have this bound here. So how do you prove that? That's an application of the bondedness, uniform bondedness theorem. That's why this exercise is in this chapter. So how do you do that? Just quick ideas, just the quick steps of the proof. You assume that that's not true. So first you want to prove that there is some constant m and some mu such that the norm, so this is the operator norm for fixed t, is less than m uniformly over t for t belonging on some interval 0 mu. We first want to prove that. So to prove that, assume that that's not the case. If you assume that is not the case, then if you take the negation of that, you got that there exists some t and mu in 0 mu such that the operator norm is more than m. So I decide to choose my m equals to n and my tn belonging to, and mu equals 1 divided by n. So from that, I got a sequence tn such that the norm of stn, the operator norm of stn, is more than n. Okay, note that as n goes to infinity, tn goes to 0, and the norm the norm of stn goes to infinity. But then I have a contradiction, and this contradiction is given by the uniform bondedness theorem, because the only assumption that I did not use is the fact that as n goes to infinity, stn of x goes to x, because S is a C0 semigroup. Okay, so if you have that, necessarily you have that the norm of stn, the x for fixed x, is finite, the supremum of all over n. This is thanks to the convergence of stn x toward x. Now, from the uniform bondedness principle, this gives you that the supremum on n of Stn, not for fixed x, but of the norm of Stn, is finite. All right, but this gives the contradiction with here. All right. Okay, there's a typo here. There's nothing here. So finally, I have that this inequality holds. So now the thing is that I looking for this estimate, which is for all t or all non-negative t. Why here I have only an estimate for the interval 0 mu. How can I express any t in function of t belonging to an interval 0 mu? I will write t equals n mu plus delta like this. So I write that, and then I use the property of the semigroup. So I obtain that. Now I take the norm, and since the norm of all this mu and delta are in the interval 0 mu, so I have this, the norm of S mu and S delta is less than m. So I got that, and then I express m as exponential of log of m. I got that, and finally I got the result. All right.